So I see a couple of people did send me in the answers. Let's see if we got them right. Remember, when it says divide and you have a polynomial divided by a monomial, what you have to do is separate and put each term of the polynomial separately on the monomial. So we have to put the 8y5 over the 4y to the third, plus the 4y to the third over the 4y to the third, minus the 6y over the 4y to the third. When it says divide, it didn't say reduce, it didn't say simplify, it said divide. They want each term divided individually by the divisor, which in this case is 4y to the cube. So we have to reduce each one of these fractions separately. So here the 4 will cancel into the 8 and give me 2. And the y cubed into the y5 will cancel out, and that will give me 5 minus 2y squared on top. Remember, wherever the larger number or letter is, that's where it gets left. Since the y5 was larger than the y cubed, the exponent, the answer gets left in the numerator. Notice everything canceled out from the denominator. So we're left with 1 in the denominator. Notice we don't have to put the 1 in the denominator, so we could just write this as 2y squared. Going on to our second fraction, the 4's cancel out, and the y cubes cancel out. Everything cancels out. So I'm left with 1 over 1, which is just plain 1. Don't forget, when everything cancels out, that you have to put in a 1. Don't just leave it blank. You're dividing something by itself, the answer is 1. And finally, over here, the 4 and the 6 can be both divided by 2, so that'll give you a 3 on the top and a 2 on the bottom. And the smaller exponent is just a plain y, which is y to the 1, and 3 minus 1 is 2. So I'm left with a y squared in the denominator, because that's where the larger exponent was. So my final term is minus 3 over 2y squared. I saw a couple of people got a different answer to that, but that's because you reduced it. You did not.
I think that's the problem I have. I keep forgetting that you have to divide them like separately.
I know, and you want to know something, and it's interesting that this is something that you have to really read what the instructions are, because if it just gave you the problem and there were no instructions, doing it your way would have been totally correct, Reggie. But since the instructions here were divide specifically, this is what they'd want you to do. It wouldn't be a problem on a midterm or a final if you had this problem, because they would only give you the answers that make sense for the rule. In other words, they wouldn't give me 2 answers that, like your answer was really correct in terms of just simplifying. They wouldn't give you an answer that's correct for simplifying in that. So you would have seen that this is what they wanted you to do. I know this is just really a technicality, because your answer was correct in terms of simplification. It wasn't correct in terms of dividing. And a lot of books don't make a difference, and therefore it happens to be this particular text and this our course. This is what they require. You okay with that?
Yeah, sure.
Okay. All right, so let's just go back to what's more important, and actually is dividing a polynomial by a polynomial. We had done a couple of those. I want to do a couple more and then give you one to try, and then we'll go on to say we're finished with chapter 5 and go on to chapter 6. So the last thing on chapter 5 is dividing a polynomial by a polynomial. We're not going to go divide by anything more than a binomial. So basically, we're dividing a polynomial by a binomial. Let's say I gave you this example. 6x to the third plus 19x minus 19x squared minus 2. We want to divide that. It happens to be a polynomial with 4 terms by the binomial 2x minus 3. And if you recall what we had said on Thursday, we had said that what we have to do is something called long division. We have to set it up like a regular long division, putting the divisor, which is the 2x minus 3, on the outside of our division sign, and our dividend, what we're dividing into, inside the division sign. Now, there's something you have to be very careful about, something that is sort of an automatic when it's just plain numbers. You have to make sure that everything is in descending order. Descending order means highest power, next highest power, next highest power. If you look at this polynomial on top, our highest power is 6x to the third. But the next highest power is not 19x, it's minus 19x squared. We have to rearrange the terms so they are in descending order. Then the 19x and then the minus 2. So that's something you have to be very careful about. Make sure you're dividing into something that's in descending order. Now, I'm going to remind you of the steps that we took. Our first step in long division was to divide. That was the first thing we did. And in order to make the dividing a little bit simpler, instead of dividing by the whole binomial, we just divide by the first term. We take the 2x and divide it into the 6x cubed. Divide first into first. So that's not so hard. 2 divides into 6 gives me 3. And x divided into x cubed, remember, and then we're subtracting our exponent, is going to give me an x squared. So the first thing I get by dividing the 2x into the 6x cubed is 3x squared. What I do is I take what I just put on top, and it doesn't matter where on top I put it. I take it and I multiply by it. That's my second step. I'm going to multiply the 2x minus 3 by the 3x squared. So 2x times 3x squared is going to give me 6x to the third. And 3x squared times negative 3 gives me negative 9x squared. That was our second step, is to multiply. The third step is to subtract. We're going to subtract our original thing by what I just put on below it. In order to do the subtraction, I think the easiest way, given that these are algebraic expressions, is to use the changing of the sign method. This is a positive 6x cubed, so I'm going to change it to a negative. This is a negative 9x squared, so I'm going to change it to a positive. And then I'm just going to combine 6x cubed and negative 6x cubed cancel out. The next term, negative 19x squared combined with positive 9x squared, the negative 19 and the positive 9 give us negative 10x squared. Now you know why it's so important that we rearrange the terms, because when I multiply, I got an x squared here, I needed to go it to go under the x squared term, not underneath the x. Okay, but after I've done the subtraction, the last step is to bring down the next term. The next term I see is a 19x, so I'm bringing down the 19x. And I go right back to the start, and I divide. I take my first term, the 2x, and divide it into the negative 10x squared. Again, first term into first term. 2 into negative 10 is negative 5. X into x squared, we subtract the exponents and we get just plain 5x. So what I put on top just now was a negative 5x. What I multiply by what I just put on top, which is the negative 5x. Don't forget that negative. So negative 5x times 2x is negative 10x squared. And negative 5x times negative 3 is positive 15x. Now I've multiplied, so now I have to do the subtraction. And now to do the subtraction, I'm going to change my signs. This negative is going to become a positive. This positive is going to become a negative. And negative 10x squared and positive 10x squared cancel out. Positive 19x minus 15x gives me 4x. And bring down the next term, which is negative 2. And start the process again. 2x into 4x. So the 2 into the 4 gives me 2. And the x's cancel out. So I get just a plus 2. Don't forget, x into x cancels out. So I take the 2 that I just put on top and multiply by it. 2 times 2x is 4x. 2 times negative 3 is negative 6. I now have to subtract. So this is going to become a negative 4x, and this negative 6 is going to become a positive 6. The 4x and the negative 4x, you see how that first thing is always canceling out, and I'm left with negative 2 plus 6, which is positive 4. This is our remainder. And my answer then becomes, our quotient is 3x squared minus 5x plus 2 with a remainder of 4, or better, or more likely to write the answer 3x squared minus 5x plus 2 plus 4 over 2x minus 3. This is very often how the answer is written, with the quotient and the remainder put over the divisor. Again, you'll know which way they want you to give the answer by the choices they'll give you. Sometimes I've even seen problems like this. What is the remainder after you divide? Of course, you have to do all the division in order to get the remainder is 4. So your quotient, the answer is the 3x squared minus 5x plus 2. The remainder is 4. It's called division with remainder. Okay, let's do one more like this. And we'll see if we can, and then I'll give you one to try to make sure you know how to do it. Suppose I gave you 6x to the third minus 4x plus 7 divided by 2x minus 2. It happens to be off the sheets that I put on the weekly folder. Okay, again, we have a trinomial on top, a binomial, we're dividing by a binomial, we must do it by long division. So I'm gonna put the 2x minus 2 on the outside. And on the inside, I'm gonna put the 6x to the third, that's the highest power, so that goes first. And the next thing I'd expect to see would be an x squared term, because after x cubed usually comes an x squared, and there's no x squared term. In other words, we don't have any x squared terms. But for long division, it's important to put in every term. So what we write is plus 0x squared. There aren't any x squareds. I can't put in plus x squared because that would mean 1x squared. So we put in 0x squared. When I say we have to have it in descending order, not only do we have to start with the highest power, but every term has to be accounted for. If there's a missing term, we put it as 0, like the 0x squared, it's sort of a space maintainer. We need it to keep the spaces for the x squareds. Then, of course, the next term would be negative 4x, and the next term would be 7. And we do exactly what we did before. We divide our first term into our first term. So 2x into 6x cubed gives me 2 into 6 is 3x squared. My first term is 3x squared. I take that and multiply it by the whole binomial. 3x squared times 2x is 6x third. 3x squared times negative 2 is negative 6x squared. And that's why you'll see why it's so important for us to put in this 0x squared, because otherwise, remember, I want my like terms to be under each other, and there'd be no place for this x squared term. Okay, we now did we're up to the subtraction. So this 6x cubed is going to become a negative. The negative 6x squared is going to become a positive. And when we combine the 6x cubed and the negative 6x cubed, they cancel. And when I have the 0x squared plus the 6x squared gives me 6x squared. And I bring down my next term, which is negative 4x. And I proceed like I did before. 2 into 6 is 3. X into x squared is x. So 2x into 6x squared is 3x. I take that 3x I just put on top and multiply by it. 3x times 2x is 6x squared. 3x times negative 2 is minus 6x. And again, I'm going to be subtracting. So this is going to become a negative, and this is going to become a positive. 6x squared and negative 6x squared again cancel. Negative 4x plus 6x gives me positive 2x. And I bring down my next term, which is the 7. And I divide the 2x into the 2x. So the 2 goes into the 2 and the x goes into the x. Everything cancels out, so I have to put a plus 1. Don't forget, it's not a 0, it's a 1. I multiply by the 1. 1 times 2x is 2x. 1 times negative 2 is negative 2. And I change my signs. This becomes a negative. This becomes a positive. 2x and negative 2x cancel. 7 plus 2 gives me 9. And 9 is my remainder because there's nothing more to bring down. So we take plus 9 over 2x minus 2 as my answer. So just be careful about making sure everything is in descending order and everything is accounted for. If there's a missing term, you have to put a 0 in that place so that you maintain the space like we did here for x squared. Okay, if there are not any questions, then I'm going to give you one to try while I take attendance. Do I always what? Do you always? When subtracting, you always change the sign of the gamma. Do you always change the sign of the denominator? You're always changing the sign of the bottom one, the one, it's not the denominator, you're changing the sign. When after you multiply it, then you're going to be subtracting, changing the sign of the bottom number, because that's what we call the subtrahend, the thing that you're subtracting. Yeah, you always change the sign of the bottom one. Okay. All right, let's do another. I'm going to give you one to try yourselves. Okay, so here's an example. Eight x to the fourth minus 70, this is on the sheet also, 70x squared minus 9, and we're dividing that by 2x minus 6. Okay, it's an 8x to the fourth minus 70x squared minus 9. Okay, while you're doing that, I'm taking attendance. I hope you all received the email. I sent everybody an individual email with basically it's a progress report. I figured out everybody's average up until right after the midterm. Now, obviously, it's not your final average for the course because the final average will consist of not only the midterm, it'll consist of the final as well. The midterm and the final together are 60% of your grade, but 40% of your grade is classwork, homework, tests. Now, if you're missing any tests, if you're missing homework, it's going to affect your final grade. And if you look at your grade and it's not as high as you think it should be, it's probably because some of your homeworks are missing or one or two of your tests are missing. If anything is missing, make sure you make it up. If you're missing a midterm or a test on Blackboard, which you no longer will be able to see on Blackboard, email me and we'll decide on a time when you could take that test, and I will set it up for you. But you have to understand, you have to let me know because you can't just let it go. If you're missing tests or if you're missing homework, the homework on Delta Math is really available the whole term. But the tests on Blackboard, once the due date is gone, it doesn't appear on Blackboard anymore, but I can always open it up for you if you are missing something. So you will be able to tell right away by your grade whether something is missing or not. So if it is, make sure you make it up. Most of the grades were very good in this class. Okay, so I'm taking attendance now. Maury here. Chelsea. Good afternoon, Chelsea. Ariana.
Here.
Hi. Adina.
Here.
Hi. Lachey.
Here.
Hi.
Hey.
Tava, I know you're here because I spoke to you.
Yeah, I'm here.
Terrence,
Here, good afternoon.
hi, good afternoon. Karide,
Here.
did you see that note that I sent you?
No, I didn't.
I look at the chat. I sent you a chat.
Okay, I see.
Yeah. Okay. Kezia,
I'm here.
good. Faith. Faith D.
Here.
Hi. I have you absent a lot of times, but you're doing great in the course. Are you absent or you just don't hear me calling your name?
Sometimes I'm absent, but I usually watch like the videos that she posts on Blackboard. So when I do miss a class, I'm able to watch it.
Let me just mention, I do not use attendance to lower your grade. If you're doing well in everything and you watch the videos, well, that's fine. The participation is part of the grade. What I do is I use it to raise somebody's mark. If somebody's been in class and always answer questions and send in the answers on the chat, there are people who do this on a regular basis. And let's just say that person's average was an 88. Now, an 88 is really a B plus. It's not a, I would probably give that person an A or an A minus for the course. So I use participation and attendance to raise your grade if it helps. So I just wanted that to be, you to be aware of that. Because what I sent you in the email was strictly nothing, and it was just strictly what your average is at this point. Ethan. Good afternoon. Isabella.
Here.
Hi. Serenity. Reggie. Now, Reggie, I know I spoke to you.
Here, good afternoon.
How are you? Zamia. Hi. Brandon. Brandon Hernandez. Michaela.
Here.
Hi. Seraphine.
I'm here.
Good. Marissa. Hi. Renee.
Here.
Hi. Sky. Jaden. Shelton. Kennedy Shelton. Kennedy. Kennedy here. Felicia. Hi. Natalia.
Here.
Hi. Michael.
Here.
Good afternoon. Cassidy. Hi. Megan, Kalia, Lauren,
Here.
hi,
Hi.
and Kayla Zachary. Kayla Zachary, okay, let's do this and see what we come up with as an answer. All right. So the first thing I'm going to do is I'm going to put the 2x minus 6 on the outside. And on the inside, oh, I have an x to the 4th, so that's my highest power, 8x to the 4th. The next thing I'd expect to see after an x to the 4th is an x cubed, but there's only an x squared. So I have to put in a space maintainer for that. So there are no x cubes. Then I put in the negative 70x squared. And after the x squared, I should see a plain x term, and there's no x term. So I'm going to put in a 0 for that as well. Notice, if my first term was an x to the 4th, I should have 5 terms. 4, 3, 2, 1, and no x's. So now I have it set up so I can do the problem. It's going to be a long problem because there's so many terms. I'm going to take the 2x, divide it into the 8x to the 4th. So 2 into 8 is 4. Remember, the exponents we're subtracting, so 4 minus 1 is 3. So the first term on top becomes 4x to the 3rd. I take that 4x to the 3rd and multiply it by both terms. 4x cubed times 2x gives me 8x to the 4th. And 4x squared x to the 3rd times negative 6 is minus 24x to the 3rd. Okay, so now I'm going to subtract. And remember, I do that by changing the signs of the second binomial here. This is going to become a negative, and this is going to become a positive. So the 8x to the 4th
I'm
minus.
trying to win on my money.
Sorry? Was there a question?
No.
Oh, okay. So the 8x force cancel out. And now I have a 0x cubed plus a 24x cubed which gives me 24x to the 3rd. And I bring down the next term, which is negative 70x squared. And I now start my dividing again. 2x into 24x cubed. So 2 into 24 is 12. And subtracting the exponents, 3 minus 1 is 2. So this becomes 12x squared. I take that 12x squared that I just put on top and multiply by it. 12x squared times 2x is 24x to the 3rd. You see, the first term always should be the same thing that it is, so it cancels out. Then we have negative 6 times positive 12x squared, which gives me negative 72x squared. These numbers are getting big, so you can certainly use your calculator to do the multiplications. Okay, we're subtracting, so this is going to become a negative, this is going to become a positive. And the 24x cubed minus the 24x squared cubed cancel. And now I have a negative 70x squared and a positive 72x squared, which gives me 2x squared. And I bring down the next thing, which is just 0x. And I start again. 2x into 2x squared. So the 2's cancel out, and the x into the x squared just gives me 1x, or just plain x. So I put a plus x on top, and I multiply by that x. So x times 2x is 2x squared. And x times negative 6 is negative 6x. And now I'm subtracting again. So this is a negative, this becomes a positive. The 2x squared and then 2x squared cancel, 0x plus 6x gives me 6x. And I get a minus 9. Bring down the minus 9. So now I divide the 2x into the 3x. So the 2 divides into the 6 and gives me 3. And the x's cancel. Don't forget the x's cancel. So I'm left with 3 on top and multiply everything by the 3. 3 times 2x is 6x. 3 times negative 6 is negative 18. And again, I'm going to subtract, so this will become a negative, this will become a positive, the 6x's cancel out, negative 9 plus 18 gives me 9 as my remainder. We can either write it remainder 9, or we can put plus 9 over 2x minus 6. So that was a really long problem. It didn't look so long when we started it because but once we realized that we were missing terms and we had an x to the 4th, they'll never give you anything this long on a final. But if you can do this, you can do anything. Okay. Reggie, that was excellent. You really got that right. Great. Okay, so I think we're at the point where I think we understand this division. This takes care of chapter 5. We're now going to be doing chapter 6. Once we finish chapter 6, we'll have a test on chapters 5 and 6 together. So let's go on with this, and let's talk about what is chapter 6 all about. So the title of chapter 6 is basically, well, one part of the title is radicals. It's also about something called fractional exponents that we're going to do a little bit later after we talk about this whole concept of what a radical is and how to deal with radicals. Now, there is a symbol that looks like this. This is what's called a radical sign. It looks like a division sign, except it has a check mark. And when you see that, it's indicating that what they want you to do is to find the square root of the number. If I write this radical 25, this could be either read radical 25 or square root of 25. Now, what am I asking you to do when I'm asking you to find the square root? I'm asking you to find the number that when you multiply it by itself will give you 25. The square root of 25 means what number times itself gives you 25. And if you think about them, there actually are two numbers. There's 5, and there's also -5, because 5 times 5 is 25, and -5 times -5 is also 25. Now, that could be very confusing if you had one symbol and it could have two answers. So we always use this radical 25 to indicate what's called the principal square root of the number, which means the positive square root. So when I write the square root of 25, I mean 5. Yes, two numbers multiplied by themselves give you 25, 5, and -5, but the principal square root, the one that we mean by the word square root, is 5. So, now, there are a couple of things we should know about this. First of all, as we said, this is the principal square root. We always take the positive square root. Also, for real numbers, the number system that we are using on a general basis, which is called the real number system, you cannot do the square root of a negative number, because there's no number, no real number that when you multiply by itself will give you -36. Can't be +6, because positive times +6 is 36, positive 36. And -6 times -6 is also positive 36. So to say you want the square root of -36 in the real number system, the number system that we use for almost all types of computation, this is not something that's possible. We're going to see later in this chapter, there is a number system that is sometimes used, not very often, but it is sometimes used, where it is possible to do this square root of a negative number. It's called the imaginary numbers, but that's for later in the chapter. Right now, this is not something that we can do. Now, this radical sign is not used just for square roots. It's used for other types of roots as well. Sometimes you'll see something like this. There'll be a number inside that check mark. That number is called the index of the root. This is read the third root of -8, or the cube root. Sometimes the term used is cube root. But when you see that index of 3, instead of looking for a number times itself, what you're looking for is for a number times itself 3 times. That will give you -8. Now, when the index is an odd number, then it's possible to have a negative inside the radical, because -2 times -2 is +4, and +4 times -2 gives you -8. So it is possible to have negatives in roots where the index is an odd number, like this cube root or the third root or the fifth root. Those can have negatives inside the radical. For when your index is even, like a square root, even though no number is written in it here, when there's no number written in it, it's understood that the index is 2. If it's 2 or 4 or 6, then you can't have a negative inside there. Then you're not going to have a real number. It's very important to have the calculator handy from this chapter on, because a lot of the square roots you can only do if you have a radical, if you have a calculator. So if you haven't been using your calculator up until now, and you haven't been bringing it to class until now, now would be a good time to start, because absolutely from now on, you're not going to be able to do these problems without the calculator. Now, suppose I was giving you something like this, the square root of 50. What do we do when the number inside the radical is not a perfect square? What do we mean by a perfect square? A perfect square is a number times itself. Like 25 is a perfect square because it's 5 times 5. And 64 is a perfect square because it's 8 times 8. And I assume that you know the perfect squares until about 15. For example, 169 is a perfect square because it's the square root of 169 is 13. So I assume you know those. If you don't, make sure you use your calculator as much as possible and get familiar with them. So if you look at the square root of 50, now the square root of 49 is a perfect square. The square root of 49 is 7. And the next perfect square after 49 is 64, because the square root of 64 is 8. But there's no exact number that is the square root of 50. If you put this 50 into your calculator and you try to find the square root of 50 on your calculator, and I assume everybody knows how to do this, in my calculator, it's a matter of pressing second and x squared, I'm putting in 50. The answer I get for this when I put it in my calculator is 7.071067812. That's what I see. Oh, actually, that's not even an exact answer. The reason it stops right here is because my calculator has only positions for 10 digits. It's a 10-digit calculator. I won't get an answer with more than 10 digits. If you read this, there are 10 digits here. Really, this thing goes on and on. If I had a calculator that had room for 100 digits, it would go on for 100 digits. 1,000,000 digits, it would go on for 1,000,000 digits. This is a non-ending, non-repeating decimal. What do I mean? Well, non-ending, we understand what it means. What do I mean by non-repeating? There's no pattern here. It doesn't go 7.070707, which would be repeating the 07 endlessly. There's no pattern there that I can discern. When you have a non-repeating, non-ending decimal, that is something that's called an irrational number. An irrational number is one that doesn't have an exact square root. So, going back to this, the square root of 50 is irrational, which means that its answer is unending and non-repeating. What can I do with something like that? Well, depends what I want to use it for. If it's just somebody's using it for a practical purpose, they need to measure something, well, our measurements are not that exact anyhow, so we could just round it off. Let's say call it 7.07. Now, obviously that wouldn't be an exact answer, but it'd be close to a good answer. If you multiplied 7.07 by itself, you get 49.985, which is pretty close to 50. It wouldn't be exact, but you could get a pretty close answer. That's fine for a contractor, a scientist, somebody who isn't in what we call the exact science. Mathematics is an exact science. So we would like to do something else. Not that we don't ever do this, but usually instead of getting the decimal rounded off version of the number, we do something that's called simplifying the radical. What do we do by simplifying a radical? We break the number up into two numbers that multiply to 50, and one of the numbers has to be a perfect square. Now, if you think about it, 50 can be broken up into 25 and 2. 25 times 2 is going to give us 50. So the square root of 25 times the square root of 2 is going to give us the square root of 50. Now notice the 25, the number I put in front, is a perfect square. The square root of 25, you can always take the square root of a perfect square. That's a rational number. Square root of 25 is 5. So this could also be written as 5 radical 2 or 5 square root of 2. That is what's called simplifying the radical, by breaking it down so that the number inside the radical is as small as possible. If you figured this out on your calculator and you figured this out on your calculator, you'll see that in decimal form, they're exactly the same value. This is what's called the simplified version. And that's what we mostly do. We don't go to decimal form, we go to simplified version. We want to get as small a number in the radical that we could possibly get. What if we have a variable inside a radical? What do we do with that? So let's say I had the square root of x to the 10th. We're going to put it all together in a second. When we have a variable, it's even easier to take the square root than it is with the numbers. Because when you're taking the square root of a variable, what you do is you divide the exponent by the index. Now, when it's a square root, the index is 2. So 10 divided by 2 is 5. This is x to the 5th. That makes sense, because if you take x to the 5th and multiply it by x to the 5th, it's going to give you x to the 10th. If I had something like this, the 5th root of x to the 15th, this means I'm looking for a number multiplied by itself 5 times to give me x to the 15th. Again, with the exponent, I divide by the index. 5 divided by 15 divided by 5 is 3. So this becomes x to the 3rd. And notice if you multiplied x to the 3rd times 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 x to the 3rd, you would get x to the 15th. So working with the variables is in a way easier than working with the numbers themselves. But what happens, okay, let's go back to our square roots. Even though I'll occasionally mention a cube root or a 4th root or a 5th root, really what we're interested in this chapter is square roots. What are we doing with this square root? So let's go back to the square root. And what would happen if I had something like the square root of x to the 7th? Now, according to my rule, what I should do is take the 7 and divide it by 2. But when I divide, since 7 is an odd number, I'm going to get either a fraction, 7 over 2, or 3.5, or a decimal, 3.5. And that's certainly not considered simplest form. We will be discussing what fractional exponents mean. That's part of this chapter. But really, when we don't want to leave answers in their simplest form. with fractions or decimals in their exponents. So what we do with something like this is we break it up, just like we broke up the 50 into 25 and 2. What we're going to break this up into is two factors, where one of them is going to be a perfect square. And in order for a variable to be a perfect square, what it needs is to have an exponent that's even, because then I can divide it by 2. So what I'm going to do is I'm going to break this x to the 7. I'm going to just take 1 away from that exponent. I'm going to break it up into x to the 6 and x. Certainly x to the 6 times x certainly gives me x to the 7. And this x to the 6 is now a perfect square because its exponent is even. So now I'll divide the 3 by 2. We'll get x to the 3rd outside the radical times radical 6. So that's what we do when it comes to simplifying radicals with variables. Make sure that if your variable doesn't have an even exponent, break it up into 2 parts, just subtracting 1 from it. Let's put all this together. Let's say I gave you something like this. Square root of 48, a to the 5th, b to the 8th. Let's say I wanted to simplify this radical. So that means I have to break it up into 2 radicals. I'm going to separate this into 2 parts. The first part is going to be a perfect square part, so I'll be able to take its square root. And the second part is going to be everything that's left over. So the first thing is I look at the number, the 48. Now, there actually are a couple of ways to break up 48 so that one of the numbers is a perfect square. 48 could be either 4 times 12, 4 is a perfect square. It could also be 16 times 3, because 16 times 3 is 48, and 16 is a perfect square because it's 4 times 4. When I have more than one choice, what I want to do is pick the larger one, because what I want to be left with in my radical is as small as possible. So I'm going to pick for the 48, the 16 in the first radical, the perfect square radical, and the 3, because that's what's left over. Now I go to the letters, the variables. A to the 5th. It's not a perfect square because its exponent is odd. So I subtract 1 from it. 5 minus 1 is 4. So I put a to the 4th in the first radical. And a, just plain a, or a to the 1, and the second radical, because a to the 4th times a is a to the 5th. Then I go to the b's. The b to the 8 is a perfect square. It doesn't have to be split up because its exponent is already even. So I just put the whole b to the 8th in that first radical. So I'm left in my first radical with 16a 4th b 8, and on my second radical 3a. Now that this is a perfect square, so I take its square root. The square root of 16 is 4. And remember, the exponents I'm dividing by 2, so that's going to be a squared b 4th. That's in the coefficient of the radical 3a. This would be our answer. Now you might say, oh, it doesn't look any simpler than what we had before. This is a technical term, and simplifying radicals means what you're left with is as small as possible, what's inside the radical. These are outside the radicals. You're not doing square roots of this. You're just going to be left with the square root of 3a inside. The 4a squared b 4th is now outside the radical. Okay, now the reason we spend time learning how to simplify radicals is because of the rule for adding and subtracting of radicals. I'm going to give you the rules, and then I'll give you some to try on your own. When you have two radicals, like the radical 3 plus radical 5, you can't add them. You can't say this is radical 8. You can't say this is square root of 8. It doesn't work. You could try it on your calculator and see it doesn't work. It's not the right answer. The only type of radicals you can add are what we call like radicals. It works just like algebraic expressions. You can only add like terms. The letter parts have to be identical. You can then you can add or subtract the numbers in front, the coefficients. The same thing is true with radicals. I can subtract something or add something like this: 7 radical 3 plus 10 radical 3. These are like radicals because the radical parts are identical. It's like x's. So the way I add them, depending on if this is a minus, I'd be subtracted, is I just work with the coefficients, the numbers in front. 7 plus 10 is 17. So the answer here is 17 radical 3. So in order to add or subtract radicals, we can only do it if we have like radicals. And that's why it's so important to know how to simplify radicals, because sometimes the radicals don't look like they're alike, but after you simplify them, they actually are like radicals. Let's take an example like this. Suppose I gave you 2 radical 75 minus radical 48 plus 3 radical 12. And I said, here, I wanted this simplified. I have 3 terms, I want to simplify it. And I look at it initially and I say, can't do, they're not like radicals. The numbers inside the radicals are different. If there are letters, then they'd have to be the same also, just like terms. But let's see if we could simplify each of these radicals. Sometimes after we simplify them, there might be some that are like. It might not all 3 be the same radicals, but maybe 2 are alike and another one is different. As it stands, we can't do anything. We have to simplify. So the first thing I look at is this 75. I want to simplify 75, so I'm going to break it up into 2 radicals. The first thing I think about 75 is obviously 25 and 3, because 25 is a perfect square. So I'm going to break the 75 into 25 and 3. The square root of 25 is 5. So the square root of 75 becomes 5 radical 3. Now don't forget, I had this 2 on the outside. I have to now take that into consideration. Rule: you can never take a number that's outside a radical and multiply it with something that's inside a radical. The only way you can multiply is when you have outsides by outsides and insides by insides. Now, if I look at this 2, which is outside the radical, can now be multiplied by this 5 that is also outside the radical. I couldn't multiply it before, but now I can. 2 times 5 will give me 10, and this gives me 10 radical 3 as a simplification for 2 radical 75. Now I look at the 48. And we did 48 before. We got the 48 we broke up into 16 and 3. And the square root of 16 is 4. So this becomes minus 4 radical 3. And finally, we have this 3 radical 12. So the radical 12, again, I can break up into 4 and 3 because 4 is a perfect square. So now this becomes 2, the radical 12 becomes 2 radical 3. Now I multiply that 2, which is outside the radical, with the 3 that's outside the radical, and that gives me 6 radical 3. So now I've simplified all my radicals, and lo and behold, I have like radicals, so now I can combine them. Remember, I only look at the numbers in front, the coefficients. 10 minus 4 is 6. 6 plus 6 is 12. So the final answer to this is 12 radical 3. And that would be considered simplifying this expression or combining the radicals, whichever you want to call that. Let's see if I can give you one to try. Okay, so we have this 5x radical 8 plus 3 times 32x squared minus 5 times square root of 50x squared. See if you can simplify this expression. Okay, let's see if we can do this now. We want to simplify it as it stands. Well, there's nothing to combine. But we want to simplify our radicals. This radical 8, I'm going to break up into 4 and 2. And the square root of 4 is obviously 2. I can multiply the 10x by the 2, so that first term becomes 10x radical 2. Okay, now I have this 32x squared. Let's see what we're going to do with that. Well, obviously, the 32 I'm going to break up into 16 and 2. And the x squared is a perfect square, so I'm going to put that next to the 16. So this 16x squared, that's at my perfect square, becomes, when I take its radical, is 4x. Radical 2 stays here. And now I have to multiply that 4x by the 3 that was outside of there originally. So this becomes 12x radical 2. Now we're at that last term, the 50x squared. Well, the 50 I'm going to break up into, we've done that before, 25 and 2. And again, the x squared is a perfect square because it's got an even exponent. So that'll go with the 25. So this will give me 5x radical 2, but there's this 5 over here that I have to multiply. The original 5 on the outside now multiplies with the 5x that came out of the radical, so that becomes minus 25x radical 2. And if I look at it now, these are all like terms. The radicals are the same and the variables are the same. The only thing that's different are the coefficients, so I add them. The 10 and the 12 give me 22. 22 minus 25 gives me negative 3. So this becomes negative 3x radical 2. So we see that it is very important to be able to simplify these radicals, because then we can add or subtract them. Somehow I didn't get the same answer as you did. Reggie, oh, there was an X here in the front one. Reggie.
Yeah, I just noticed that.
Okay. Otherwise, your answer, if it wouldn't have been there, your answer would have been correct. Yes. Okay. So now we know how to add and subtract radicals. Let's at least start talking about multiplying of radicals, and that's where we'll start on Thursday with multiplication of radicals, but I just want to get started a little bit. It's at least the basics. So we said it's impossible to add or subtract radicals unless they are like radicals. The numbers inside the radicals have to be identical, and then what you combine are the numbers on the outside, what we call the coefficients. Well, what happens if we're multiplying radicals? So I'm first going to start just with what we call monomials. Let's say I have something like 3 radical 10 times 5 radical 20. What's the rule for multiplication of radicals? Well, number one, you can only multiply a square root with a square root. You can't multiply a square root with a cube root. In other words, the indices have to be the same. And then the rule basically is take the numbers that are outside the radical and multiply them together. So multiply the 3 times the 5 and get 15. And then multiply the numbers inside the radicals, the 20 times the 10, those can be multiplied together. You can never multiply a number that's outside a radical with a number that's inside the radicals. Outside numbers by outside numbers, insides by insides. That's why when we were simplifying before, we were very careful. We only multiplied the number, the coefficient on the outside once there were other numbers outside. We never took something that's outside a radical and multiplied it with a number that's inside a radical. Now, this is the answer, except we usually like to write our answers in simplest form. So after I've done the multiplication, what I want to do is I want to see if I can simplify the 200. And obviously, what I can break up the 200 into is 100 times 2, because 100 is just 10 times 10. The square root of 100 is 10. And now this 10 is outside the radical, so I multiply it by this 15 that's outside the radical, which is 150 radical 2. And that would be my answer in simplest form. Again, they want us to give our answers in simplest form. Okay, let me give you one to try, and then you'll look for homework on Delta Math on this. What if I gave you this? Okay, I'm going to give you, it's 5 radical 3x to the 5th times 2 radical 12x to the 7th. And give me a minute to try that. Karide, I sent you a text. Okay, that'll work for you?
Yes.
Good, excellent. I'll open both of them at that time, both tests, because you were missing another test also. Okay, I see we have an answer already. Let's see if we can do this together. So the first thing I'm going to do is multiply the numbers that are outside together. 5 times 2 is 10. And then I'm going to multiply the numbers that are inside together. So here I have a 3 times a 12, which is a 36. And an x fifth and an x seventh, which when I'm multiplying variables, I add their exponents. So that gives me x to the 12. And I want to simplify the radical. And guess what? This is a perfect square. 36 is just 6. And x to the 12th is also a perfect square because its exponent is even. This is 6x to the 6th outside the radical. So now I'm going to multiply by 10. 10 times 6x to the 6th gives me 60x6. No radicals at all. And that can sometimes happen. You start out with 2 complicated radicals, but when you multiply them, you got a perfect square inside your radical, so you were able to simplify it. Yes, that was correct, Reggie. That was excellent. Okay, so we're going to stop here. We're going to continue with multiplication of radicals and then go on to division of radicals next time. And if there are any questions, don't forget to look at your Delta math for any homeworks that and make sure you keep current with the homeworks. And also, if you didn't see it yet, I did send out to each person individually their grade in this course up till now. Obviously, that's not your final grade because there's still a final going on, and I sent it on the email that I always use for sending you emails. It's the one that you have listed on Blackboard. That's my only email that I know of you. It's the email address that you gave me, that you put on Blackboard. That's how I communicate with you. So if you didn't get it, and either look at that email address, it's important for you to access it, probably the MEC email address. And if you can't find it, then just send me an email and I'll resend it to whatever email address you want it to. But basically, the way I send emails to this course, in this course, is I go to Blackboard and there's a send email tool, and that's how I send it, whatever you have listed on Blackboard. Okay, so as I said, Natalia, I don't know what you have listed on Blackboard. Again, if you didn't get it and you're looking for it, just send me an email and I'll respond to that email I'll send it on that email. But basically, you have to know that when I'm sending out emails, and I'm sending out emails about the course all the time, it's going to the email that's listed on Blackboard. So if you want to get the emails from this course, you have to open up the email that you listed on Blackboard. It's very important because it's my only means of communicating with you. Not just talking to you, Natalie, but to everybody. Make sure you look at your email. I think I certainly send an email before each class reminding you that the class is going to be taking place. So I've sent out hundreds of emails to this class. And if you haven't gotten any, it means that you're not looking at the right email address. Okay. Do me a favor, email me. Oh, you just added another email. But in the meantime, if you want, send me an email to my email address saying you want the grade, and I'll send it. I'll forward it to you at that email address. Okay. Have a good day, everybody. I'll see you on Thursday. And we'll continue with our discussion of radicals.
Have a good day, Professor.
Bye-bye.